Okay. Okay, as you should be able to see. By the way, if anybody has any questions, please speak up because I cannot see your comments or anything while I am presenting in this mode. Okay. So if you have a question, stop me, ask me, unmute and ask me. And remember to unmute, of course. Now, as you can see, this is an old slide. It was from the time I gave this course 3 years ago. But thankfully, the topic is something which will not change much in those 3 years. So this is still relevant. Now, the first slide here is basically an advertisement. And I'm sure it's really not necessary for most of you, but still, why do we study ODEs at all? ODEs, of course, is short for ordinary differential equation. So we study them because they're the most important mathematical structures in science. Dynamical systems in physics are described by second order equations of motion. That's one of the most important uses of it, where the mass times acceleration is given by force, which typically depends on position, velocity, and time. Well, despite the fact that there is a second order differential equation, we can easily recast this in two coupled first order equations. dx dt equals p by m. That of course defines momentum for you. P by m is of course velocity. And dp dt is the force, which is of course the original form of Newton's second law. Now the reason why this is important is that solving first order differential equations numerically is a lot easier than solving second or higher order differential equations. However, the important thing here is you can always recast higher order differential equations in terms of several first order differential equations. So if you study how to handle first order differential equations properly, especially systems of first order differential equations, not one, but maybe several, then any higher order differential equation can also be handled numerically. There are many subtle points, and we are going to explore some of those subtle points here. So more generally, this is the system that you have already studied, of course. The canonical equations of motion, where qi dot and pi dot are derivatives of the Hamiltonian with respect to pi and minus qi respectively. And again, you can see that even if you have more than one degree of freedom, you would have q1, q2, q3 up to qn and p1, p2, p3 up to pn. So you'll have 2n first order differential equations describing the system. Now, we are going to stick to ODEs in this lecture and maybe throughout the next one and the first one next week. So we will essentially stick to these issues for the time being. We are going to talk about partial differential equations, which in a sense are infinite number of ODEs, in the lecture after that. Okay, so, well, this was a bit of advertisement for other disciplines, but we don't really need them so much here, although, frankly, many of you would work in biophysics and models like this, and nonlinear dynamics, of course, uses this a lot. So anybody who takes a nonlinear dynamics course would definitely meet the Lotka-Volterra model. And the Lotka-Volterra model is a situation where you have a prey population X and a predator population Y, that is, say, rabbits and wolves. And the basic idea behind this equation is really rather easy to figure out. I'm not going to go and describe the whole thing now, but you should be able to figure out why, for example, dx dt equal to alpha x would simply mean that the prey population, say the rabbit population, grows in proportion to the number of rabbits which are there, simply because of procreation. On the other hand, the rabbit population declines because wolves eat them, and basically that would be proportional to how many wolves get to eat them. Okay, so, and how many encounters occur And basically, what we are looking at is a situation like this, that if you have more, so the number of wolves times number of rabbits is the probability of wolves encountering rabbits, and in a fraction beta of that, you end up with a wolf eating a rabbit, so you get minus beta xy. Well, the more the wolves get to eat, the more they grow. So that's why you have a delta xy term. Well, the wolf population by itself would die out because without anything else to feed them, they will simply not have enough to eat and die, and that's why you have a minus gamma y term. But this is a nonlinear set of equations, basically because of the presence of the xy term, and that gives rise to a lot of interesting features. And anyone who has already studied a bit of nonlinear dynamics would know this, or at least next semester you will definitely take a course. Some of you will definitely take a course in this, and you will find that there are many interesting things that can happen here, which can teach you about other branches of science as well. Well, in chemistry, of course, you have the reaction rates equation and so on. All of these, the basic reason behind saying this is all of these can be handled using differential equations, coupled set of differential equations. That's it. So let's try to solve such an equation. At least you should all know that you cannot really solve a differential equation as it stands. You have to either give additional information in the form of initial values or in the form of boundary values. Boundary values are more complicated. We are going to handle them next week. This week we are going to concentrate on the initial value problem. So, as I said, first order differential equations are what we will study. There are special techniques for higher order differential equations, but some of them are useful, but most of them can be sort of bypassed simply because, as I said, higher order differential equations can be written down in terms of coupled first order differential equations. And by the way, I know that most of you will be coding in Python using hopefully NumPy and SciPy. Some of you are going to code in Fortran. Unfortunately, say generalizing a result from one differential equation to a bunch of coupled differential equations is trivially easy in NumPy. It's not so easy to code in Fortran. It's not very difficult. It's just that in NumPy is actually trivial. You have to do almost nothing, as you will see when I come to code examples. In Fortran, on the other hand, it takes some amount of work to do it right. So that you will have to suffer for if you are coding in Fortran. Unfortunately, that can't really be helped. But I'm not going to try to scare you. Fortran is perfectly capable of handling these things. And if you do not see how easy it is to do it in NumPy, you would not really miss that. So don't worry too much if you are only going to do in Fortran. And for most of you who are going to use NumPy and SciPy, the job is going to be much easier. That is the actual coding job. But the theory behind the differential equations, which I'm going to describe today, is of course come quite independent of the programming language that we are going to use. Okay, so what we are going to discuss is a first order differential equation of the form dy dt, which is given as a function of y and t. And this is subject to an initial condition. That's why it's called the initial value problem. At some initial time t0, y is given as y0. And you should be able to figure out what y is at a later time from this. So the simplest algorithm that we use here is something which I'm pretty sure all of you have seen before. At least all of you who did the previous computer courses here would definitely have seen before. All you do is you take a step size h and say that, okay, if I know y at time t plus h is simply more than y of t by this quantity. And what is this quantity? This h is simply the time interval, and f is simply the derivative at the beginning of the interval. Right? You're saying at time t, take the value of y, take the value of t, and calculate f with that. That, of course, is the derivative at time t. So what you are doing in the Euler algorithm is you are approximating the rate of change between t to t plus h by the derivative at the beginning of the interval. What you really need for an exact calculation would be the average rate of change over the interval from t to t plus h. But what you are using is basically the derivative at the very beginning. Now, this is something which all of you should be familiar with. In fact, this is basically the definition of the derivative used as an approximation, nothing more than that. So at this stage, I'm not going to describe the Euler algorithm in great length because this is supposed to be obvious. But is there any question about this? So let me just check that first. Anybody has any questions about this? And once again, it's better if you speak up.
Sir.
Yeah.
Sir, this h is like is the difference between say t0 and t1. Like I know t0 at t0 the value of the constant is y0.
That's a okay. So what this h really would be a small time step. Okay, if as you will soon see, the error in this method depends drastically on h. The bigger h is, the bigger the error is going to be, and you don't really want a huge error, right? So suppose you are given the value at t0 and you want the time at say some later time t1. In principle, you can take h to be t1 minus t0. Okay, but then h will be very large, and as a result, what will happen is that the error in the method is going to be very large. Well, you can easily understand that, right? What you are saying is the rate of change itself could very well be a variable, right? So if you take the rate of change at the very beginning to be the rate of change throughout, almost certainly you're going to make a huge error, except in the very special case when the rate of change is a constant. So if I go back to lapse into physics language, if velocity is fixed, then of course you can write velocity times time interval as a change in position, always, as an exact statement. When velocity is not fixed, if you replace the velocity at the beginning of the time interval if you use the velocity at the beginning of the time interval as a velocity throughout the interval, you of course are going to make an error. And in fact, what we are going to do is we are going to estimate what that error is and why this is big and so on. So if you want to use this method, what you would want to do is use a small time step. That means instead of going from t0 to t1 directly, you will first go to t0 to t0 plus h. Now what that does is that now you knew y at t0. Now you know y at t0 plus h. You can use that to find out the derivative at t0 plus h. Using that, you can go to y at t0 plus 2h. Then using that, you can go to y at t0 plus 3h and so on until you reach t1, where t1 is your final value. Okay. So usually, if you have a finite time interval over which you want your solution, which usually you would not actually do it in one go. You will break it up into many pieces and use those pieces. Now, in principle, by making the h small enough, you can always reduce the error in an individual step to arbitrarily low values. Okay. So if your computers had really been capable of infinite precision calculations, then our course would have ended here, because we would have said, okay, all I want is some reasonable degree of accuracy. So if I take a step size of say 1 unit, I may not get that accuracy. What I will do is I will break it up into 10 pieces and go 10 times in step size of 10. That will reduce the error. If that doesn't reduce the error enough, I will reduce it further by breaking it down into smaller step size and so on. So in principle, the Euler algorithm is all you would have needed. Just use the Euler algorithm, nothing else. that will tell you everything that you want, right? The problem with that is, of course, that your computer only calculates to finite precision, as you have all seen in the previous part of the course. The very method by which computers store floating point data is inherently problematic. It will definitely give you errors. Okay. And as a result, what will happen is that you are going to accumulate more and more errors the more steps you take. First of all, taking many steps is going to slow down your program, which used to be a huge concern earlier. Today, maybe not so much because we have very fast computers. But even then, taking 20 times, say 100 times longer to solve a problem is not really a great idea. And the other important thing is, even if you had arbitrarily huge amount of time, so you could afford to calculate over many steps, the real problem would be every time you do a calculation, you incur a tiny error. That error may be tiny, but if you do it over many steps, that error would accumulate and become large. Okay, this is the reason why you have to learn more numerical analysis at all. Otherwise, just Euler algorithm and that's it. You don't need anything else. Unfortunately, things don't work that way. You need to learn more advanced algorithms primarily because they help you to cut down at the expense of some amount of more work. They help you to cut down the error per step. As a result, you can afford to use bigger time steps. I'm saying time here simply because I'm using t as a variable. You should, of course, understand that this t could be any dependent variable and y could be any independent variable. Sorry, t could be any independent variable in the problem. And y could be any variable which depends on that. So this is the motivation for doing whatever I'm going to do in the rest of the course. Okay? Is that okay with everybody?
Yes, sir.
Okay. So let's come back to the steps here. Okay. What I do is I use a sort of concise notation. Instead of saying y at t plus h, I label the time intervals by n, and I say y at t plus h is approximately y at t plus h f y t comma t becomes y at n plus 1 is yn plus h times f at yn comma tn. Okay, where of course tn is t0 plus nh. Counting, of course, starts from nth count starts from 0. So y0 will be where you start, that's at t0. Then y1 is at t0 plus h and so on. Now this notation, of course, is trivial, but it will help us to write many of the things more concisely later, when you have more complex expressions. So it's important that you are aware of what we are doing here. Now, I'm not going to prove this at this stage, but it should be sort of obvious that the local error or error per step for the Euler algorithm is of the order h square. Well, it's actually obvious because if you actually wrote down y at t plus h using the Taylor series expansion, what you would get is y of t plus h times f at yt comma t plus h square by 2 factorial times, the second derivative of y, which is of course first derivative of f, and so on. And since you're ignoring the h square by 2 term, which would have come here in the Taylor series, of course, the local error, which is error that you are incurring in every step, is order h square. So if you cut down your step size by a factor of 10, your error gets reduced by a factor of 100. Doesn't sound too bad, but you have to realize that if you use a smaller time step, then to get to the same final time, you will have to use more time steps. So the number of time steps will be actually inversely proportional to h, which means that the error, global error, that is the error which you incur when you go from t0 to your final time t1, is actually going to be of order h, because it's order h square per step times the number of steps, and the number of steps is 1 by proportional to 1 by h. So this means that ultimately, in the Euler method, if you want to cut down the error in your final result by a factor of 10, you have to increase the, you have to decrease the time step by 10. You don't get to do much better than that. So if your error is too big, you have to go in for a very, very small time step with the other problems that I outlined. You will take more time. Also, you will incur a lot more error because of round of errors. Remember, these local error and global error calculations are basically mathematical errors. These are errors which occur because your algorithm has not taken into account the full mathematical formula involved. Okay, clear? So this is assuming that the calculation can be done to infinite precision. It's just that you have dropped higher order terms. But in reality, you have these kind of error as well as errors because of round off errors in calculation because of the finite precision and so on. So you have to, there's always this interplay between these two problems, and they usually work in opposite directions. So when you decide on a good algorithm to use, you have to understand that there is this conflict between the two things that you want. You want the thing to be done fast and with less error, and these two things may often have a conflict. So that's how you get to decide what to use, and that's why you need higher order algorithms. Okay, this thing is really a trivial statement which looks a lot more complicated than it is. It's simply saying that if you, instead of having one first order ODE, you have several, let's say n first order ODEs, y1, y2, y3, yn, where your independent variables, and dy1, dt was function 1 of y1, y2, yn, and t, and dy2, dt was function 2, and so on, then yi at t plus h will simply be yi at t plus h times f of yi at the beginning of the interval. So basically the same idea. You have n distinct independent variables here. I hope this n will not be confused with this n here. This n is actually the nth time step. This n is of course n variables. I should have perhaps used different notation here. But anyway, the basic idea is when you are going from the ith time step, when you are trying to figure out how the ith function changes from t to t plus h, what you are just using is the slope of the ith function at the beginning of the time interval. This is just for how the Euler works. We will actually have Euler as an exercise, not because it's a good method, but because it's reasonably good even for many purposes. And more importantly, it's going to help you contrast with what you gain when you go to the higher order, more complicated algorithms. So that's what we are going to discuss now. Improved methods of integration. Okay. So now, basically, the improved methods basically start by understanding what the Euler algorithm does. This is exactly what I've told you so far. The Euler algorithm uses the derivative at time tn as an approximation for the rate of change over the entire interval from tn to tn plus h. So ideas, well, how can I improve on this? Can anybody tell me? Any suggestions as to how to improve upon this with the least amount of work? The problem is I'm taking the derivative at the beginning of the interval to be the derivative throughout. How would you think? Give me some ideas. How would you improve on this?
Take the average of the derivative of the two endpoints of the step.
Okay, that's one idea. Okay. You have two endpoints, one at tn, the other at tn plus h. Find the derivatives there, take the average. There is a problem there. We are going to come to the problem later, but anyway, that's a good suggestion. Another one? Any others? Yes? Any other suggestions other than this one? This is a good suggestion, definitely. We are going to actually use this. But any other suggestions beyond this one? None? I think another one should be sort of obvious.
Take derivative at the middle point of the step.
Sorry, I couldn't hear you. Somebody say something?
You could take the derivative at the middle point of the step.
Okay, good. That's another possibility. Could take the derivative at the midpoint of step. Right. So that's another possibility. You could take the derivative at the mid. So we will start with that, although the other suggestion is also equally good, as it turns out, or equally bad. That is, they are both improvements on the Euler method, but both of them have their own issues, and we will see how to handle them. But let's start with this one. That wouldn't it be better if we use the derivative at the midpoint instead of using the derivative at the beginning? Okay. So at Tn plus h by 2. Remember what was our differential equation? It was dy dt is a function of y and t. Now, if the function of y and t depended only on t and not on y, okay, then this would be a trivial thing to do. It would be easy to do. All you do is put in t plus h by 2, right? Tn plus h by 2. In the function, you get the answer. Clear? So yn plus 1, 10 plus 1 at y, the y at Tn plus h would just be y at Tn plus h times f, not at Tn but at Tn plus h by 2. This should be an improvement, at least looks like. We will see later whether it is, but should be an improvement. Okay, let's see it right now whether it's an improvement. Okay, so this is the mathematical part of the calculation. I want you to pay some attention to this. This is the easier bit of mathematics that we are going to do today. The rest is going to be even more difficult or more complicated, but the idea is the same. So let's look at this carefully. This is what we are claiming is yn plus 1. Okay, that's an approximation, of course, but let's try to figure out how good that approximation is. It's going to be y at Tn, fine, plus h. Now f at Tn plus h by 2 is simply f at Tn plus h by 2 times f dot at Tn, the derivative. I hope you can see the dot in the slide. Plus other higher order terms of order h square. This is nothing but Taylor series. By the way, the Taylor series is what is going to be our go-to method, go-to mathematical formula for this entire part of the course. Everything will be Taylor series in some form or the other. So here what we have done is write f of Tn plus h by 2, of course, which is a step into f dot Tn plus order h square terms. And now you realize that f of Tn is nothing but y dot, right? So you are writing y Tn plus h y dot Tn plus h square by 2 y double dot Tn. F dot Tn is y double dot Tn plus order h cube terms, because order h square here inside the bracket times the h gives an order h cube term. But this is what is very, very important. You should realize that if you take the first 3 terms sitting here, you get the first 3 terms in the Taylor series expansion of y at Tn plus h. You don't get the order h cube term, of course. At least you do have an order h cube term here, but that doesn't match the order h cube term you're going to get from here. So what you have managed to do is that your approximation for y Tn plus h is an improvement over the Euler one, because in the Euler one you really just had the first 2 terms of the Taylor series. You had an error here. In this method, what you have done, this is called the midpoint method, by the way, for obvious reasons. And in this method, what you have done is you have got y at Tn plus h correct up to 3 terms, that is up to the second order in h. So what is the error here? The error here is going to be order of h cube, an improvement over the order h square error that you had in the Euler method. Let me just remind you that this is a local error in one step. Of course, this means the global error will be order h square. Order h square is much better than order h, which means if you cut down your h by a factor of 10, your error is going to fall by a factor of 100. Okay, so that's actually not quite bad. The important thing is you should be able to get to a low error without reducing h by a huge amount, which means without having to do many calculations, without having to incur a lot of round of errors and so on. So is this clear to everybody? And can anybody spot why is this going to be difficult in general? That is, the general differential equation, of course, is not dy dt equal to f of t. We usually don't even call dy dt equal to f of t a differential equation. We just call it a integration problem, right? If the derivative is given as a function of t alone, then I know what y is. You just integrate f of t dt. That's it. Simple integration, which by the way is officially called solution by quadratures. So quadrature is simply a fancy way of saying finding the area, and you all know that the definite integral is connected to finding the area. So dy dt equal to f of t would be a rather trivial differential equation to solve. At least we have shown that if you tried the midpoint method there as opposed to the Euler method, you are going to have an improvement. But can you see why this is not so easy to do in general? Yes?
Sir, here the function is only like it's depending on t.
Yeah.
But if it was depending on both the variables y and t, then there would be some like kind of confusion.
What confusion? Yeah, you're right. But what exactly would be the problem? Remember, there's an initial value problem, right?
Initial.
What do you know?
We don't know the value of y at mid, like at tn
exactly.
plus h2.
Okay. That's exactly correct. The point is, you know what the initial value of t is, and you know the t at every time step simply because the time step is under your control. You start with a given value of t0, then you keep on increasing it by h every time. So tn is known. Y at tn is known because you've worked it out from the previous step with some errors, but at least that's something you have calculated. But how do you find out y at tn plus h by 2? You don't know that, right? That's a sort of catch-22 problem. I hope all of you here know what a catch-22 is. If you don't, read the book. Okay, but anyway, you can understand what catch-22 is even without reading the book catch-22, but it's a good book to read anyway. But the real issue is, this is the midpoint Euler method proper now, where actually we are saying the function y of t depends explicitly on y as it usually would, because unless it did, you would usually not even bother calling it a differential equation. So then what you do is you need the value of y at the midpoint of the interval. You have no way of knowing that. You know the value of y at the beginning. So what you do is you adopt a kind of hybrid approach. You say, okay, let's start with a slope at the beginning of the interval. Let's call that Pn. This is the nth interval. So time at the beginning is Tn, y at the beginning is Yn. And what we are saying is, okay, the slope at the beginning of that interval is f of Yn comma Tn. Let's call that Pn. And we are going to use that slope to go to the middle point. That is, what we really want is this. We want the value of f at t equal to Tn plus h by 2 and y at Tn plus h by 2. This is the one which we don't really know, y at Tn plus h by 2. Okay. So what will we do? We actually estimate this slope at the midpoint by this quantity Qn. This is really not the slope at the midpoint. This is our approximation to it. And how do we calculate that? We calculate that with Tn plus h by 2. Of course, there's no problem. We just put that in as a second argument, as a t argument. For the y argument, instead of putting in y at Tn plus h by 2, which you do not know, you put in the estimate Yn, which is y at Tn, plus h by 2 into Pn. So what we are doing here is using the slope at the beginning to estimate what the y will be at the midpoint, right? So because we've only moved h by 2 from Tn, this is going to be yn plus h by 2 times Pn. That's an estimate, of course, that's not exact. And then we are using that estimate to calculate Qn. Okay? And then we are going to use this Qn as a slope throughout. That is, we are going to say yn plus 1, y at the end of the interval is yn plus h times Qn. Clear? Is this clear? Is the algorithm clear?
Yes, sir.
Okay. However, you may now get into an worry here. That is because you're approximating the value of y at the middle. That of course will lead to some error. So this improvement that we are claiming that the midpoint method will give you over the Euler method, is this really going to happen? Because if you could really calculate the derivative at the midpoint, of course you would expect the Euler method to be the midpoint Euler method to be better than the Euler method. But since you can only estimate the slope at the middle and not find it out exactly, will that make a huge difference? So we really need to get down and do some hard work here to find out whether this thing actually works out properly. That is, whether the error here is really order h cube, or whether this thing that we done here has really messed it up. Okay. Now this is where the hard part begins. By the way, this slide is up on VLearn, so you, even if you can't follow all the steps right now, you should be able to do it when you take your time and read it slowly. However, I would urge you to pay attention here. This is really the basic idea behind whatever we do for the rest of the courses, at least for the rest of this part of the course. So what we are doing here is saying, okay, I have got this estimate for Qn. Now I can find out what Qn is at least 2 ordered h square simply by expanding this expression out, right? Yn, if I know f at yn comma tn, and f is a known function, so if I give it fixed arguments, I always can figure that out. So what is it going to be? It's going to be f at yn comma tn. Okay, by the way, this entire expression that you see here on these two lines is being evaluated at the beginning of the interval at yn comma tn. All I'm using is simple Taylor series. I'm saying Qn is f at yn comma tn plus h by 2 times date at which f changes with y. Well, actually, it should be del f del y times h by 2 pn, because h by 2 pn is the amount by which yn has changed. Y has changed from yn. And del f del t times h by 2. That's the first order term in Taylor series. So all we are doing is using Taylor series in 2 variables. Okay. So instead of having one derivative term times times delta x, you have 2 derivative terms. Del f del y times delta y plus del f del t times delta t. Delta t is h by 2 and delta y is of course h by 2 pn. And then we have the higher order derivative. This is something we have to calculate now, because we are claiming that our method is actually accurate to order h square. So we have to calculate the order h square derivative, which of course involves the second derivative del 2f del y2 into a square of this h by 2 pn. Okay, so h square by 4 pn square, but there's an extra half in front, so 1 by 2 factorial goes from there, plus del 2f del t2 into h square by 4 into 1 by 2, that's the Taylor series formula, plus the cross term that you have. Okay, is there any confusion about how we arrived at this?
No, sir.
Okay, fine. So this is now the algebra gets a bit messy at this stage because of the many terms involved, but the algebra is really rather simple. So it may be difficult for you to follow this on the screen. I will try to explain every step, but it's better that you actually take down pen and paper and work it out yourself. Okay. Now, this is Qn. But what we need ultimately to find out y at Tn plus h is really the derivatives of y dot, y double dot, y triple dot, and higher order derivatives at the time Tn, right? Because that's what is going to go into the Taylor series expansion for y. Y at Tn plus h will be y at Tn plus h times y dot at Tn plus h square by 2 factorial y double dot at Tn and so on. But now the differential equation tells me that y dot is f of y comma t. It also tells me y double dot is the derivative of this function with respect to t. And that of course is del f del y times dy dt plus del f del t times dt dt. Dt is of course 1, so you get that. Okay. So this much should be pretty obvious to everybody. Y triple dot, which is the derivative of this, that's a longer expression, is really not that difficult. What you do is del f del y. When you do a dt of that, you get del 2f del y2 y dot times the y dot that gives you del 2f del y2 del y dot square plus del 2f del y del t times 1 times y dot. Another term comes in because you are differentiating y dot keeping del f del y fixed, so you get del f del y double dot. Now from del f del t on the other hand, if you differentiate that with respect to time, remember del f del t is a function of both y and t, so it changes with time because it depends on time. That's the del 2f del t2 term that you have. It also changes with time because it changes with y, and y changes with time. So that's the del 2f del y del t y dot. And these two terms, of course, add up together. So what you have is a 2. And if you want to evaluate this at n, that's what you really want, right? Because these are the expressions for the derivatives in general. But in the Taylor series, what we want is the value of the derivative at the beginning of the interval when t is tn and y is yn. So y dot at Tn is simply f of yn comma Tn, which is of course what I've called Ps. Yn double dot, well, I just take this expression and put in yn comma Tn here. So it's del f del y at yn comma Tn times Pn, because y dot is Pn, plus del f del t yn comma Tn at yn comma Tn. Similarly, this other thing where all I've done really is I've put in all the y dots that we had at yn Tn. I've replaced them by Pn. So I get Pn square here, Pn here. The rest is whatever I have. Okay, this is the expression. Everybody with me so far?
Yes, sir.
Yes, sir.
Okay, now notice that if I take these expressions, if you look at this Qn, this term here, del f del y Pn plus del f del t, evaluated at yn comma Tn, is actually yn double dot at yn comma Tn, right? Yn double dot, which is y double dot at Tn. This term here in the bracket. Okay? And this term in the bracket is almost yn triple dot.
Sir, can
Is
you
it okay?
repeat?
So if you remember what we are trying to do is we are going to use Qn in the calculation when I want to estimate yn plus 1, right? The Qn I have already shown up to order h square is given by this expression. But these things in the bracket here, for example, del f del y Pn plus del f del t, notice what that is. That's actually yn double dot, right? Is that okay?
Okay, sir. Yeah.
This thing in the bracket here is almost yn triple dot. If it had been yn triple dot, I would have been very, very happy. Unfortunately, it's not. Yn triple dot has this term. So this is here, this is here. This term is also here. This term is not here. So yn triple dot is actually bigger than this, bigger or smaller depending on whether this is positive or negative. But anyway, this term is missing in this bracket here, right? So if you use that, you simply get Qn, that expression. Okay, let me just quickly remind you that this becomes Pn. So this becomes yn double dot. F of yn comma Tn is just Pn. This becomes yn double dot. And this becomes, or this is also yn dot, which is actually what is more important for us in the next step. This is yn dot. This is actually yn double dot. this is not quite yn triple dot. So what you have is this expression. Qn is yn dot, that's the f of yn comma tn, plus h by 2 yn double dot. This term exactly matches. This term is not exactly yn triple dot. If it had been, we would have been very, very happy, but it's not. And even if it had been, it would not have been perfect for us for reasons that you will soon see. Anyway, this is what Qn is. This is what we are actually using in the midpoint Euler method. So, what is yn plus 1 actually? The Taylor series tells you is y at tn plus h, which is yn plus hyn dot plus h square by 2 factorial yn double dot plus h cube by 3 factorial yn triple dot and so on. Sorry, there's a typo here. This should be yn triple dot, 3 dots rather than 2, plus order h to the 4. Here I have become a bit more ambitious, so I have written down all the terms up to order h cube now. Earlier, well, if I were doing this for Euler, I would have just stopped at order h square because I know that only order h matches. But now notice, hyn dot plus h square by 2 factorial yn double dot is actually h times qn. H times qn has those two terms, right? Is that okay? If you multiply h times h by qn, which remember is what you are going to add to yn in the midpoint Euler method, you get hyn dot, you also get h square by 2 yn double dot, but you get h cube by 8 times this, which does not match this one. Okay. So this is actually yn plus hqn plus this extra piece. That this works out to be this extra piece is simple algebra. There's a 1 by 8 which you have and a 1 by 6 which you really wanted. The difference gives you 1 by 24. That's sort of easy to figure out. Okay. So my point is, if you add to yn h times qn, the derivative at the middle of the interval, you get y at n plus 1 almost. You don't exactly, you end up getting the first order term in the Taylor series perfectly correctly, second order term also perfectly correctly. You don't get the third order term correctly. Okay. So even despite the problem that you don't really know y at the middle, and you're estimating that, the midpoint Euler method does work to the extent that it actually improves your estimate over the Euler method. The Euler method would have just given, if you had used h, in fact, here you can see what the Euler method does. In the Euler method, you just use Pn, which is yn dot, right? You estimate y at n plus 1 by yn plus hpn. So you get just the first two terms in the Taylor series, right? The order would have been h square. In the midpoint Euler method, you get this term right, you also get this term right. So the error is order h cube, and which, by the way, seems like I'm repeating something. I just showed a while ago, okay, maybe 20 minutes ago, that the error would be order h cube per step. But that would be the case. The error would be order h cube per step, but that would be the case if f had been a function of time alone. Okay. Now we have managed to show that even if f is a function of y and t both, the midpoint Euler method still works better than the Euler. It actually gets the first two correction terms in the Taylor series correctly, and only has an error of the order h cube. Of course, for some special functions, it might so happen that yn triple dot plus 3 del f del y yn double dot ends up being very small, but that's not general situation. Yeah, any questions? Any questions? Okay. So what we have managed to show is that we have improved upon the Euler method. The midpoint method has a local error of order h cube and a global error of order h square. And in the worksheets, I will give you problems where you can actually explicitly check this. That is, you can check that this method, the midpoint Euler method, gives you smaller errors for the same age compared to the Euler method. Now, is this the only way of getting this far? Of course not.
So what is
It
the
was a
global
generalization to
one order less?
What?
Why is the global
Sorry.
error one order less?
Yeah, that's what I explained a while ago. Global error means total error that you accrue when you go from the initial value of T0 to the final value T1, whatever value you want. And to get there, the number of steps you need to take. Remember, the order H cube error is for every step you make, right? The number of steps you take will be proportional to, it will be equal to T1 minus T0 by H, right?
Yes.
If H is a time step, so the number of steps you take has to be order 1 by H. Not order 1 by, it has to be proportional to 1 by H, which means that the total error that you accrue from one end to the other, that's the global error. That, of course, has to multiply the local error, what you get in every step, by the number of steps, right?
Oh.
So that's why an H cube term multiplied by 1 by H. Remember, when you say order, you don't care about what's in front. You are just saying, if I change H, how fast is that going to change? Okay?
Okay. Thank you, sir.
So that's always the case. Local error, if we manage to get a local error of order H to the 5, which will be our aim, by the way, at least, then the global error would be order H to the 4. So today, let me just point out that the midpoint Euler method is an improvement, but it's not the only possible way. In fact, a generalization to the midpoint Euler method would be the Runge-Kutta method. Okay. Well, this is not the Runge-Kutta method, which is actually the one we will use. We will use the Runge-Kutta fourth order method. Right now, we are talking about the Runge-Kutta second order method, something which only gets the Taylor series correct up to order H square. The midpoint Euler happens to be an example of the Runge-Kutta second order method, but there are other possibilities. One possibility is simply, as was pointed out, instead of using the value at the beginning or the value at the middle, you could use the value at the average of the values at the beginning and the end. By the way, all of these were basically due to Euler. So you have the Euler method, you have the midpoint Euler method, now you have the modified Euler method. The modified Euler method is take the value of the slope at the beginning, take the value of the slope at the end, divide that by 2, that is sum up and divide by 2, that is average the 2. Of course, the question would be, how do I find the value at the end? You can't really, because the value of the function depends on y and t. So t becomes tn plus h, that's fine. But what is y? What you do is you estimate what y would be by using the slope at the beginning. So you use the slope at the beginning to estimate what y would be at the end. That is yn plus h times pn. And then find f of that. That will give you an estimate for the slope at the end. Take the average of that with the slope at the beginning, and you have got the average slope throughout. And this, if you use this slope, that is, if you multiply this slope by h and add to yn to get yn plus 1, that gives you the modified Euler method. Okay. I cannot finish off the rest of the calculation today, of course, because I have only 2 minutes left. But let me just point out that what we will want to do is something more general. The more general thing is, I'm going to use Pn and Qn. Pn is the slope at the beginning. Qn is the slope somewhere in the middle, not necessarily at the middle or at the end. And you're going to weight them by 2 weighting factors, beta 1 and beta 2, and use this weighted average of Pn and Qn as the slope throughout, as an approximation to for the slope throughout. And how do you find out? Pn, of course, is f of yn comma tn, the slope at the beginning. Qn, okay, this should be Qn here. Qn is f at tn plus alpha h. So alpha is some number between 0 and 1. So instead of saying you take the slope at the beginning or the middle or at the end, you are taking slope some fraction alpha down the way. If alpha is half, of course, you're right in the middle. If alpha is 1, you're at the other end. If alpha is 0, you're of course, at the beginning. And so what you're saying is, okay, this is the t at alpha, this is a time, alpha h fraction after the beginning of the interval. And because you're saying that the time elapsed from the beginning is alpha h, you're estimating the y there by saying y at the beginning of the interval yn plus alpha h times pn. Okay. Now the aim would be to take this expression for qn, expand it out using Taylor series, the way we have done before, plug this expression into the Taylor series for y, and try to ensure that we get at least order h square correct. We will see that with this we can get only up to order h square correct. We cannot go further. We cannot get order h cube correct using this, for example. However, you may be able to understand that instead of using 2 slopes, if we had used more slopes and more points in between, and chosen the weights and positions properly, you should be able to go beyond just order h square or h cube. Okay. In fact, the thing that we are going to describe next lecture is, first of all, in the next lecture, I'm going to describe the derivation in general for the Runge-Kutta second order method. I'm not going to talk about how the Runge-Kutta fourth order method is derived, simply because it takes a huge amount of grunt work. It's not really difficult. It's just a lot of algebra that you have to just sit down and work out to work the result out. But you get the basic idea. The basic idea is, instead of relying on the slope at the beginning or at the end or at the middle, you make several estimates of the slope somewhere in the middle of the interval by using techniques like these, and take a weighted average of those slopes and try to ensure that final weighted average will be able to reproduce the Taylor series correct to order, which is much higher. So in principle, you can go to as high a order as you want, but of course, the higher the order you go to, the more complicated the calculation and the expressions become. So typically what people use is the Runge-Kutta fourth order, which I have actually described to you earlier, once at least. But we are going to try to understand why it works. We may not be able to derive the whole expression. It's not important, really. But the derivation that I will do for the Runge-Kutta second order essentially is the same for the fourth order. It's just that fourth order takes more work. So that's for Thursday. Okay, any questions? By the way, the slides are already up on the net, so you can definitely take a look at them. Even the rest of the lecture, that is the second order calculations and so on. Okay, so let's meet on Thursday, and by Thursday evening you will have your problem sheets. That is a problem sheet for this part.